right. Thank you very much for that very kind introduction. So if you just start, title of the talk is Generating Ergonomic C++ APIs using Rustdoc, Procedural macros, and Serde, not necessarily in that sequence. So first of all, a couple of words about myself. I have a degree in geoinformation science, so I left university with my master's. And right after that, I joined Giga Infosystems, and I've been with them since 2017. Towards the end of university, I first got in touch using Rust, and I'm in the fortunate position to use it at my day-to-day job. And overall, this amounts to a bit over 8 years of working with Rust now. This is also my first presentation on a Rust topic, so we're kind of pushing my comfort zone here, but I've been told that is a good thing. So let's see how this goes. If you want to get in touch, I'm on Mastodon. Currently, there's not too much riveting content there. One of the last few tweets was this one at the EuroRust team, where I asked them about 2 months ago if there was any presenters guidelines available already. So because I wanted to get a head start on my presentation. If you would have asked me a week ago, I would tell you that I did not, in fact, get a head start on my presentation, but that was not because of the EuroRust people. But let's get into this. To recap a little bit, I think most of you will be aware of this, but why are FFIs important? So FFIs, first of all, stands for Foreign Function Interface, and it basically allows code written in one language to call code written in another language. And that is specifically important for a language like Rust, which is still in the process of spreading throughout the industry, throughout use cases, because most of the time when you try to introduce Rust at your company, you won't be in the position to start a project from scratch, but you will most likely have to interface with an existing code base. And C++ is pretty popular, so this is some code that you will have to interface with on a regular. So we've written down a couple of ideal properties that we think an FFI should have. So ideally, it has a very small amount of boilerplate that you need to write, because usually we want to write code that adds functionality to something and not boring code like this. While going through this interface, it shouldn't really have a negative performance impact. And ideally, it is very ergonomic to use. That means from the Rust side, the code looks like Rust and follows the idiomatic Rust that we would assume. And from the C++ side, it looks like C++ code. So a little bit about what experience we've gained over the years at the company, also the reason why we think our experience is sort of valuable to the Rust community. So our Rust journey started already in 2016 when we decided to fully replace our C++ and SQL backend. So most of you will know that Rust got to the 1.0 stage only in 2015. So you could describe this adoption either as fearless or as foolish. You can choose one of the two. But ever since then, we have a database management system where we store 3D geoscientific data. And this is completely written in Rust. And it has to interface a lot with a desktop application that's written in C++. We also have web apps, and over the years, Rust has been introduced there as well, using WASM. And we also have at this point, I think, 2 standalone Rust helper apps, which have also found their way to our tool set that we use. Also here you can see our web app that is also using Rust already, and you can see the visualization of one of these 3D geoscientific models. So what have we used in the past? The first thing that we used was cbindgen. Most of you will probably notice. We relatively quickly moved to our own custom fork because we needed a couple of adjustments so that it would work a bit nicer with our C++ code. And we've been using this for a while. So now the issues that we had with this, the first one is kind of rather specific to us. So in general, it wasn't the best C++ code back then, but very specific to us. We had to deal with legacy string encoding. So the desktop C++ app was still using Windows encoding, and Rust and the databases all had UTF-8. And this also propagated over to the Rust side of things. So there we had to deal with string encoding And also in the interface, we had to deal with many type conversions that we had to implement manually. We had to be wary of the memory, of allocating and deallocating memory. We had to write a lot of unsafe code in our day-to-day work with the API, mostly because we had to manually handle pointers. And if you have a look at this, this does not look like stuff that you want to do while you use Rust. You know all the good stuff about Rust. You don't really want to handle these things. So we looked at, first we look at a couple of examples from code back then. So this is the Rust code, and you had, for example, a struct that you want to use in this interface. You see the primitive types are still the same, but we also have to deal with this like pointer to a char array. We have other custom types, as we call them, like GSDR color, that would have to implement conversion functions so that everything would work nicely. And most importantly, down below, you see we had to implement our own free functions. So everything that is allocated on the C++ side and comes over to the Rust side needs to be dropped there. Everything from the Rust side that goes over to the C++ side needs to be dropped there. And all of this had to be written by a programmer by hand. And if you miss anything, like the free function or the drop function that I'm going to show, the compiler is not going to complain. That's just a memory leak. And of course, people are going to forget this, even with pull requests and everything. So at the bottom, you can see also one of these conversion functions. In this case, we convert something directly to a protobuf type, which we use in the API. You see we have some string handling there. We have this one into call, which is calling one of the conversion functions. And remember, this is a rather simple API call here. And we still have to write all of this code manually. And this as well. It's not particularly difficult, I'd say, but it's not looking super nice and it's not very convenient to write. So of course we looked at other possibilities over the years. So I've kind of dug into our internal knowledge wiki and also our Git history, because over the years many people have looked at this issue and have written down their thoughts, and I've tried to collect some of them. So relatively early on, we also had a look at CXX, but we weren't really happy with the error propagation over the interface, and the enum support also wasn't fitting quite our needs. For safer FFI, we would have had to make many changes to the C++ code, which wasn't feasible. And when we first had our look at Diplomat, we relatively quickly ran into issues where certain things weren't supported yet, such as using string instructs. We also toyed around with the idea of just directly calling the protobuf API, but we also wanted to do many things in Rust code. So we needed functionality there, so that was not an option either. So we stuck with our cbindkin approach. Over the years, we tried to make it nice. We worked on error propagation. We tried to add more information, such as tracing. I thought we added a Rust API, but we actually didn't. So mind you, we only had these extern C functions that I showed you before. But this is not a pure Rust API. And I noticed when I started one of these Rust side projects, I wanted to call the Rust API. We don't have one. We only added a couple of functions. So that is really a pain point as well. And all the other issues, the dereferencing, the string handling, we tried to move it into nice pieces of code that we could reuse, but we still had the unsafe pointer handling and everything. So we didn't find a nice new solution, but we really learned what the issues were and what we would need. So again, to kind of summarize, what were our goals for this new approach? So ideally, we removed so much of the boilerplate that we would have to write. So that includes, we didn't want to deal with manual conversion of types. We didn't want to deal with manual deallocation or with weird string handling. And also the unsafe code shouldn't have to be written by the developer to add something to this API. So it should be contained somewhere safe. And of course, it should be nice and usable from the C++ side as well. And if we get to this, ideally, we don't lose too much performance. And this is where we have a look at this approach that we've taken. And as you've seen before, types in this interface create many of the headaches that we had. So especially manual type conversion, and then all the other stuff that follows. So the idea now is we replace almost all of the input types in the interface with byte buffers. And I've tried to visualize this here a little bit. So when we come from the C++ side and we call what we want to call a Rust function, we serialize all of the input arguments, where in the C API we only have byte buffers, and on the Rust side we deserialize everything again. And then from the Rust side, when we want to return a result, we serialize this result. In the C API again we only have a byte buffer, and on the C++ side we deserialize it again, and we have something that we can use in a nice and ergonomic manner. Now, the way I want to go through this process is by looking basically at the keywords from the title of this presentation. So the first step will be how we use procedural macros to generate the extern C functions that we've seen. In the second step, we use Rustdoc together with Rustdoc types to parse what we've generated in the first step. And the third step will be how we generate the C and C++ code using our understanding that we've gained through Rustdoc types with help of Serde reflection and Serde generate. And all the serializing and deserializing throughout these three steps will be handled by Serde and bin code. So let's look at the first step, how we use procedural macros. I've put together the simple example here where we have something like a test client which has any function on this that we want to call on the API, which is called greetings. So it just takes a string, formats it, and returns a result of the string. So that's relatively straightforward. And using this example, we will see how using Serde and bin code to serialize all the input arguments, these extern C functions that we've written by hand before become very, very similar to each other. So that is the perfect example where we can use procedural macros to streamline the whole process. So as you will notice, we have this API macros exported macro that we call on this implement block. And the single step expansion looks something like this. So at the top, we still have our test client, our basic function. But at the bottom, you see what was basically generated, this pub unsafe extern C function. It has a prefix now, so we have GST and GSTR as prefixes. That's just in our code base. But as you will see, the only thing that remained is this pointer to a test client. But name is not a string anymore. It's now a byte buffer with a certain size that we provide. And the result is basically the length of what we've written into this output pointer. Now, if we have a look at this function a little bit more closely, there are basically two parts of this. The first part deals with looking at the pointers that it got. So this is if this pointer is null thing, the unsafe stuff, and we throw errors if something is not right. And then the second part here is where we take our input slice and deserialize it back to a string. And this allows us to call the greetings function with the input at the end of this, and we have assert unwind safe and catch unwind to not panic if we have any errors with the pointers, or if there's a panic, we can still return a nice error. Now, after calling the Rust function, ideally, we get a result from it when all the pointers were right. We grab this result, use bin code again to serialize it, get the bytes, write the bytes into the output pointer, determine the size of this, and return this length at the very bottom. So I forgot that this was the proc macros sidetrack, and I thought I could make people happy if I say there's no more proc macros after this. And that's why I put the slide, but it's not really appropriate anymore. Okay, just moving on. We now have our extern C functions without writing one line of this, which is already really nice. Now we need to still generate the C API, the raw C API, and the C++ types and functions. And in order to do this without anything else, we need an understanding of what functions we want to add to this interface, what types are required, and whether part of such an implement block for a test client, or if they are freestanding, like not associated with anything. And if we go back a little bit, no, sorry. First, if I usually don't understand a thing about Rust code, I just go to docs.rs, and for a crate, such as Rustdoc types, all the types and structs and enums and functions and trait implementations are listed there. As most of you will know, this is the output of Rustdoc, the HTML output, but Rustdoc also has an unstable JSON output format. And this is much nicer to work with compared to HTML. And there's also a crate called Rustdoc types, which takes this JSON output and puts it into a nice to work with like structure, tree-like structure, where you can go through and find all of the things again, resolve types between crates. And this is basically what we do. We generate this JSON for our own crates. And then if we use types from external dependencies, you need to declare them as well. And we generate the documentation for this. Then we do some magic and then we're done. Okay, let's look at the magic part. First of all, a little look at what Rustdoc JSON looks like. In this case, for our greetings function, you can see what name it has, which crate it belongs to, where it is located in the file, if it's public, if it has documentation associated with it. But you can also see all the input and output types. So here for the output, we see it has a result. And if you would, if there would be enough space, there would also be in the type section the string that we had, the result string. Now we only have to find the relevant functions, right? Excuse me. So we have created the documentation for everything in our own crates and these external dependencies. If we go back a little bit, the proc macro expansion also had this little configuration where it won't compile if we set generated extern impl. This is kind of a trick here because we never set this. We only use it as a marker because that shows up in the Rustdoc JSON as well. And we can figure out, okay, which implement blocks do we need, which functions do we need, and we just gather all of them together. Now this is really a kind of messy process. For us, it was a very iterative process, but still to resolve all of these functions, all of these types, we had to do a lot of work to go through this Rustdoc type structure. But at the end of the day, if you have everything together, you can turn it into Serde reflection types, which is kind of neat because you can take them and put them into Serde generate, which generates all the C++ types for us, including serialization and deserialization. So that's really straightforward. And yeah, for the C API and for the C++ functions, we have to do something else. So here's just how simple it is at the end of the day with Serde generate. You just throw in your registry of types that you have, say, okay, I want the encoding with it as well, have the Serde runtime, have the bin code runtime, and then you have all of your results. For the raw C API, the declarations are simple enough. We can create it by hand, like automatically by hand, but write the code ourselves. And for the C++ functions, they look very similar to what we've created on the Rust side with the extern C functions. So it's okay for us to write these as well. And at the end of the day, we create a couple of files. So the first few ones, they're all related to bin code and Serde. They're automatically created, as I've shown you. The bottom four are more interesting. So one, the C API is stored in a file called API functions. This is the C API that I've shown you where everything is a byte buffer. Then any custom types that we have that are not primitive or string, they're stored in a types file. And then we create one file for each of these implement blocks that we have, in this case, test client. And in there are all the C++ functions with their actual input and output types again on the C++ side, and the necessary serialization and deserialization code. Any function that's not part of such an implement block will go into the freestanding functions file. Now, how does this look for a simple example? Here we have the raw C API. As you can see, again, we only have byte buffers. So that is not really usable. Or it is usable, but you would have to do the serialization yourself. But it's not very convenient in that manner. But the C++ side is more interesting, and hence we have a test client holder, which holds the test client pointer, of course. But then we have the function here, and you can see the return type is a string again, and the input is a string again. And we basically do somewhat the same as we do on the Rust side. We serialize the input, prepare the output pointer, call our function gstr greetings, and then when we get the result, we deserialize it to a bit of a weird looking type here, result string serializable error. Actually I can enhance again. String serializable error, which we're going to have a look at in a while. Also, anything that was returned by Rust, we free directly. We don't have to care about that. And at the end of the day, we only have to check, is the result okay, or if it's an error. So for the results and the errors, we have these custom types. So for result, it was this result string serializable error that you've seen. That's basically the explicit type if you have this result generic, and basically holds an okay and error variant. And it implements the same kind of deserialization as all the other types. And for error, we have this custom type serializable error, which for us holds additional information such as tracing or any other data that we could use. But ideally in the future, this should be replaceable by anything that you would need. Now let's have a short look at a more complex example. So we still have our test client. This time it has a field that has this runtime. So you will probably know what's coming. We have a more complex return type, a return type. It has a bool, and it has another one that's called option, or that is of option box, a return type. So we have some kind of cyclical dependency going on already, which makes things more difficult. And then in our function, we just return a result of a return type. If we have a look at a prod macro expansion, the first half, basically everything looks the same, but this time, oh God, I forgot it. The most important bit, it's also an async function. The prod macro expansion looks kind of the same. As I mentioned, the most important bit is now we need this runtime that we have on our test client to block on the future and resolve this. And this is basically how we need to handle the async functions. If we go to the C++ side, we now need to have this custom struct here. And you can see we have our return bool, and then we have something that's an optional of a value pointer of a return type, which represents what we have on the Rust side. So it's not like pure C++. There's these Serde dependency that you have to import and use, but that's much nicer to use than before. Also, we have these serialized and deserialized implementations. I don't want to go into too much detail either, just here so that everything is in place and shown at least once. We have the serialized and deserialized functions, and for the serialized, it looks like this, where we basically have a serialized call for the return bool, for another one, for the fields basically of it. And all of this will be generated automatically. Now, if we have a look at the C++ function, it's basically the same as before. This time we don't have an input parameter, so this bit is missing, but we just call our function over the API, get our result. This time it's result a return type serializable error because it's a different return type, but outside of this, it's basically the same. I wanted to add just a couple, like two very small benchmarks as a baseline for comparison only. Well, yeah, I've done a benchmark for a string clone call, which takes like 14 to 15 nanoseconds. And for a function that only takes a string over the API and just returns the same string, the serialization and deserialization took about like 105 nanoseconds. And for our use case, as soon as we add a network layer, as soon as we add actual work in this Rust function, this basically becomes a non-issue for us. I had a short talk with someone at the speakers dinner who said this might be an issue for high-performance computing, but this is not something that I know about. So But you have to see, of course, what kind of data you're moving around and what your use case is, if that might be interesting to you. And yeah, to showcase what happens as soon as you do a little bit of work, if I compare this with a format call, the ratio between the two already comes down significantly. So to summarize, this loss of performance is basically one of the two downsides that we can see with this. The other is that you don't have a directly usable C API. But other than that, for us, it has so many upsides. So we don't have this custom string handling anymore. Granted, that is an issue just for us, but it's completely eliminated on the Rust side. We don't have to deal with these type conversions anymore. We don't have to write unsafe code if we want to add something to the API. We don't have this manual pointer handling or manual deallocating of memory, which is just so much better on the Rust side. Of course, currently this is tailored to our needs, especially the bit where I said we iterate over the Rustdoc types information, but that does not mean that we think this can be universally applied and helpful to the whole community. For us, it would mean we need to clean up the code before we can publish it, and then we would kind of have to rely on the community of rely on interested people to give this a go, see where it breaks, and then we can handle this new cases that don't work yet. Would we recommend this for production? The thing is, we use this for a couple of months now. For us, this has been deployed on customer instances, and it's running very nicely. So from this perspective, it works really well. One of the kind of issues is that the Rustdoc JSON output is not stabilized. So you still have to use the nightly toolchain, which makes it a bit more cumbersome. So if that would be stabilized, that would be really nice. If you want to see when this comes out eventually, hopefully, you can follow me or Georg on Mastodon. We also have our GitHub, Giga Infosystems GitHub, where this would be released eventually. You can also just write me an email if you want to get in touch, or, there's still today and tomorrow. Just approach us at the conference if you want to talk about this. Yep, thank you very much.